Welcome to this walkthrough of problem number 1289, Minimum Falling Path Sum 2. In this session, we'll explore how to solve this interesting problem step by step, covering multiple approaches and their complexities. Let's dive in. In this problem, we are tasked with finding the minimum falling path sum in a given nxn integer matrix called grid. A falling path starts at any element in the first row and ends at any element in the last row. The key requirement is that as the path moves down row by row, it must shift to a different column in the next row. This means that if the current position in the path is at column J, the next position must be in a column K where K is not equal to J. The goal is to calculate the minimum sum of all such valid paths that meet this condition. The input is the matrix grid, and the output will be a single integer representing this minimum sum. Now, let's look at an example to better understand the problem. Consider the matrix grid as shown: 2, 1, 3, 6, 5, 4, 7, 8, 9. One possible falling path with a non-zero shift starts at the element in the first row and second column, which has a value of 1. From there, we move to the second row, specifically to the first column, with a value of 6. Finally, we move to the third row and last column, which has a value of 9. By summing these values, we find that the total path sum for this example is 13. Breaking this example down further, the total sum is calculated as 1 from the first row, 6 from the second row, and 9 from the third row, which adds up to 13. Now let's consider another example. If the grid contains only one element, such as 7, there is only one possible path, and the path sum is simply the value of that single element, which is 7. These examples demonstrate the problem's constraints for smaller matrices. In a slightly more complex example, consider the grid 2, 2, 1, 2, 3, 3, 2, 3, 4, 4, 3, 4, 5, 5, 4, 5. A valid falling path begins at the first row, third column with a value of 1. From there, it moves to the second row, first column with a value of 3, then to the third row, second column with a value of 4, and finally to the fourth row, third column, again with a value of 4. Adding these values together, the total sum of this path is 1 plus 3 plus 4 plus 4, which equals 11. This shows how we can calculate the falling path sum even for larger grids. Finally, let's discuss some edge cases. For a single element matrix, like 5, the output is straightforward, 5, as there's only one element. If all elements in the matrix are negative, such as -1, -2, -3, -4, the minimum path sum would still be the path with the least negative value, which in this case is -7, following the path -2 to -3. For very large matrices, such as 200 x 200, it's crucial to ensure that the solution is efficient and can handle the constraints. We should also consider cases where the matrix contains duplicate values, like 1, 1, 1, 2, 2, 2, 3, 3, 3, where the minimum path sum would be 6, following the path 1 to 2 to 3. Each of these scenarios helps in understanding the problem's scope and ensuring the solution is robust. To solve the minimum falling path sum 2 problem, let's start by considering different approaches. The first is the brute force method. This approach follows the simplest intuition: try all possible falling paths starting from any element in the first row and recursively explore all valid paths down to the last row. The only restriction is that no two consecutive rows can use the same column. For implementation, you would use recursion with backtracking to sum the values along each path, keeping track of the smallest sum encountered. However, the major downside is its computational feasibility. The time complexity is factorial in nature, specifically O(n). *n, due to the sheer number of column permutations and recursive depth. While easy to understand, this method is highly inefficient, especially for larger grids, as it involves many redundant calculations. Next, we move to a basic dynamic programming solution. Here, the intuition is to store the minimum sums of falling paths in a DP table. For each cell, you calculate the minimum sum to reach it by considering all valid cells in the row above except the one directly above it in the same column. The transition relation for this is simple: the current cell's value plus the minimum of all eligible cells in the previous row. The complexity here is O(n) cubed, where updating each cell involves an O(n) operation to find the minimum value. While this eliminates redundant recalculations from the brute force approach, it still suffers from inefficiency due to the costly operation of finding the minimum for every cell. Finally, we arrive at an optimized dynamic programming approach. Instead of recalculating the minimum for each cell in O(n), we can dramatically speed this up by pre-computing the smallest and second smallest values in the previous row. This allows us to use the smallest value directly unless it happens to fall in the same column as our current cell, in which case we use the second smallest value. This optimization significantly reduces time complexity while maintaining the clarity of the problem's solution. In the optimized dynamic programming implementation, the key is to maintain variables that store the smallest and second smallest values of each row as you iterate through the grid. The transition relation here is refined to account for these pre-computed values. For any cell, I, j, the value is updated as the sum of the current grid value and either the smallest value from the previous row, or the second smallest value if the smallest happens to be in the same column. This drastically reduces the overhead of recalculating the minimum for every cell. With this approach, the time complexity comes down to O(n squared). Since we process each cell in constant time by leveraging the pre-computed smallest values, the algorithm achieves optimal efficiency. This makes it scalable even for larger grid sizes. The trade-offs with this strategy are minimal. By optimizing the way we handle minimum value computations, we reduce the processing time without compromising the simplicity or correctness of the solution. Now, why did we choose this approach as our final strategy? The optimized dynamic programming method stands out because it leverages the problem structure to eliminate redundant calculations. The insight here is recognizing that the minimum values in the previous row are frequently reused, and pre-computing them avoids repetitive work. This makes the solution both elegant and efficient. Compared to brute force or the basic DP approach, this method strikes the perfect balance between clarity and computational performance, which is ideal for competitive programming scenarios. The conclusion is clear: the optimized dynamic programming approach is the best solution for this problem. It efficiently handles the computational challenges by leveraging the grid structure. By minimizing redundant calculations and maintaining clarity in its implementation, this method achieves an impressive O(n squared) time complexity. Additionally, it's space efficient, especially when using rolling arrays for the DP table. This strategy not only scales well for larger inputs but also maintains simplicity, ensuring that the solution is both practical and easy to understand. With no significant trade-offs, this approach provides the most effective balance between efficiency and readability, making it the ideal choice for solving the minimum falling path sum 2 problem. The problem we're solving here involves finding the minimum falling path sum in an n(x)n matrix of integers. A falling path begins at any element in the first row and, for each subsequent row, moves to an element that is either directly below, below left, or below right. This process continues until the last row, and we calculate the sum of the chosen path. Our goal is to determine the falling path with the smallest possible sum. To start, the brute force approach involves exploring every possible path starting from each element in the first row. For every valid path, we compute its total sum and keep track of the smallest sum encountered so far. While this method provides a solution, it is highly inefficient due to its recursive nature and the repeated calculations it performs. The brute force algorithm can be broken down into 3 main steps. First, the base case: if we're already at the last row, we simply return the value of the current cell since there are no further rows to explore. Second, for any cell, I, j, we recursively calculate the sum of the falling paths that pass through the cells directly below, below left, and below right in the next row. Finally, we add the value of the current cell to the minimum result obtained from these recursive calls and return it. This process is repeated for all potential paths, making it very computationally expensive. To complete the brute force approach, we need to consider all possible starting points in the first row. Since the falling path can begin at any element in the top row, we iterate over each element in that row. For each starting point, we use the recursive function to calculate the minimum falling path sum for paths originating from that cell. As we iterate, we compare the results from each starting point and keep track of the smallest sum encountered. The final result is the minimum sum obtained from all these calculations. In terms of implementation, the pseudocode shows how the recursive function works. The function find_min_path takes the current cell, I, j, as input. If we're at the last row, we return the value of that cell directly. Otherwise, we recursively compute the sums for the paths going directly below left, and below right. For the below left and below right paths, we check if their indices are within the matrix bounds. Finally, we add the current cell's value to the smallest of these recursive sums and return the result. The main function iterates over all columns in the first row, calculates the minimum falling path sum for each starting cell using find_min_path, and updates the overall minimum. This straightforward approach ensures we cover all possible paths, but the inefficiency of recalculating results for overlapping subproblems is a significant drawback. The brute force approach has a major limitation in its time complexity, which is 3n² in the worst case. This exponential growth arises because each cell in the matrix spawns recursive calls for up to 3 potential paths, leading to an overwhelming number of recursive computations as the matrix size increases. This inefficiency is tied to the fact that the algorithm repeatedly recalculates the minimum path sum for the same cells. For instance, if multiple paths share a common cell, the result for that cell is recomputed separately for each path, leading to significant redundancy. This makes the approach highly impractical for larger matrices, such as when n is in the order of 10,000. Another issue is the depth of recursion. For large matrices, the recursive calls can lead to a deep call stack, potentially causing stack overflow. These factors highlight the need for optimizations to make the algorithm scalable. From a data structure perspective, the input matrix is used as a read-only structure since its values remain unchanged during the computation. Additionally, the recursive calls rely on the implicit stack provided by the call stack to keep track of intermediate states. Addressing these inefficiencies will require techniques like memoization or dynamic programming, which we'll explore shortly. To overcome the inefficiencies of the brute force approach, we can use optimization techniques such as memoization and dynamic programming. Memoization involves storing the result of the minimum falling path sum for each cell, so we don't recalculate it multiple times. This significantly reduces the redundant computations and improves the efficiency of the algorithm. Alternatively, we can adopt a dynamic programming approach, which eliminates recursion altogether. In this bottom-up method, we iteratively compute the minimum falling path sum starting from the last row and working upwards, reducing the time complexity to n². This approach is computationally efficient and avoids the risk of stack overflow. It's also important to consider edge cases. For example, if the matrix contains only one row, the result is simply the minimum value in that row since there's no falling path. For a single column matrix, the result is the sum of all elements in the column since there's no choice but to follow a straight path downward. The algorithm should also handle matrices with negative values correctly, ensuring the minimum sum accounts for both positive and negative integers. Finally, for an empty matrix, the algorithm should return 0 or provide an appropriate error message, depending on how the problem is defined. By addressing these edge cases and leveraging optimizations, we can create a robust and efficient solution to the problem. Here, we begin by defining our function, min_falling_path_sum, which takes in a 2D grid as input. First, we calculate the size of the grid, n, which represents the number of rows and columns, since it's a square grid. We then handle an edge case. If the grid is empty, meaning there are no rows, we simply return 0, as there is no falling path to calculate. Next, we initialize variables to track the minimum and second minimum values from the previous row, as well as the index of the minimum value. These are set to infinity and -1 initially because we haven't processed any rows yet. To get started with the calculations, we determine the minimum and second minimum values for the first row of the grid. As we loop through each column in the first row, we check if the current value is smaller than our prev_min. If it is, we update prev_second_min to the current prev_min, then set prev_min to the smaller value and update prev_min_index to the current column index. However, if the value isn't smaller than prev_min but is smaller than prev_second_min, we update only prev_second_min. This ensures we have both the smallest and second smallest values in the first row, which will guide our calculations for the subsequent rows. After processing the first row, we begin iterating through the rest of the rows, starting from the second row. As we process each row, we initialize variables cur_min, cur_second_min, and cur_min_index to track the current row's minimum and second minimum values, as well as the index of the minimum value. These are reset to infinity and -1 at the start of each row. For each column in the current row, we calculate the total falling path sum by adding the value in the current cell to either prev_second_min or prev_min, depending on whether the current column matches the index of the previous row's minimum value. If the indices match, we use prev_second_min to avoid reusing the same column value, otherwise, we use prev_min. Once we calculate the total for the current cell, we update the current row's minimum and second minimum values. If the calculated value is smaller than cur_min, it becomes the new minimum, and the previous cur_min is shifted to cur_second_min. We also update cur_min_index to the current column index. If the value isn't smaller than cur_min but is smaller than cur_second_min, we adjust only cur_second_min. After processing all columns in the row, we update the previous row's minimum and second minimum values, as well as the index, to the current row's values. This ensures that the next row's calculations are based on the most recent data. Finally, once all rows are processed, we return prev_min, which holds the overall minimum falling path sum for the grid. Here, we begin by importing the necessary classes and defining our solution class. The method min_falling_pathSum takes a 2D grid as input. First, we retrieve the length of the grid and handle an edge case where the grid might be empty. If it is, we simply return 0. Next, we initialize variables to keep track of the minimum and second minimum values from the previous row, as well as the index of the minimum value. These will help us efficiently calculate the minimum falling path sum row by row. To start, we calculate the minimum and second minimum values for the first row of the grid. By iterating through all the elements in the first row, we identify the smallest value and update prevmin and prevmin index. If another value is smaller than the current second minimum but not equal to the smallest, we update prev_second_min. This setup ensures we have the necessary values to proceed with the following rows. Now, we move on to processing the remaining rows of the grid. Starting from the second row, we iterate over each row using a loop. For the current row, we initialize variables to track the minimum and second minimum values, as well as the index of the minimum value. Within this row, we examine each element to calculate its potential contribution to the falling path sum. If the column index of the current cell matches the index of the previous row's minimum value, we add the second minimum from the previous row to the current cell's value. This ensures we do not reuse the same column as part of the path. Otherwise, we add the previous row's minimum value. As we calculate these values, we update the current row's minimum and second minimum variables accordingly. This allows us to efficiently track the smallest and second smallest sums for the current row. Finally, after processing all the elements in the current row, we update our previous row's minimum, second minimum, and minimum index to reflect the values from the current row. This prepares us for the next iteration. Once all rows have been processed, the overall minimum falling path sum will be stored in prevmin, which we return as the result. This approach ensures an optimal solution by avoiding redundant calculations and utilizing the minimum and second minimum values to efficiently compute the path sum, all while adhering to the constraints of the problem. Here, we have a simple 2x2 grid as our input. The goal is to compute the minimum falling path sum with the constraint that no two adjacent rows share the same column index. First, we initialize some variables, n is the size of the grid, and we start with prev_min and prev_second_min set to infinity, which will help us track the smallest and second smallest values in the previous row. We also initialize prev_min_index to -1, which will track the column index of the smallest value. Moving to the first row, we iterate through its elements to identify the minimum and second minimum values. For the first element, which is 2, we update prev_min to 2 and set prev_min_index to 0. For the second element, which is 1, we find that it's smaller than the current prev_min, so we update prev_min to 1, prev_second_min to 2, and prev_min_index to 1. At the end of the first row, the smallest value is 1 and the second smallest is 2, with the smallest value located in column 1. Now, for the second row, we reinitialize variables for the current row cur_min, cur_second_min, and cur_min_index, all starting as infinity or -1. We begin iterating through the second row next. For the first element in the second row, which is 3, we add prev_min to it since its column index is different from prev_min_index. This gives us a value of 4, which becomes our new cur_min and sets cur_min_index to 0. For the second element, which is 4, it shares the same column index as the previous row's minimum, so we instead add prev_second_min to it, resulting in a value of 6. This value updates cur_second_min since it's smaller than the current value of infinity. At the end of the second row, the smallest value is 4, the second smallest is 6, and the smallest value is in column 0. With no more rows to process, the final output is simply the minimum value after processing the last row, which is 4. Now, we move to a slightly larger example, a 3x3 grid, to better understand how the algorithm scales. In this 3x3 grid, we begin by processing the first row. The smallest value is 1, the second smallest is 2, and the smallest value is located in column 0. For the second row, we calculate the falling path values for each column. For column 0, we add prev_second_min because it doesn't share the column index with the previous row's minimum, resulting in a value of 6. This becomes the new cur_min, with cur_min_index set to 0. For column 1, we add prev_min, resulting in another value of 6, which updates cur_second_min. For column 2, adding prev_min gives a value of 7, but it doesn't affect the current minimums. At the end of the second row, the smallest value remains 6, with a second smallest value of 6 as well. In the third row, we calculate the values similarly. For column 0, the path sum is 13, making it the new cur_min. For column 1, the path sum is 14, updating cur_second_min. For column 2, the path sum is 15, which doesn't change the minimums. After processing all rows, the smallest value in the last row is 13, which gives us the final output. Lastly, let's look at an edge case with a single element grid. In the case of a single element grid, there's only one row and one column to consider. We initialize the size of the grid as 1 and the tracking variables for the minimum and second minimum values as before. When processing the first and only row, the value at column 0 is 5, which means the minimum becomes 5 and prev_min_index is set to 0. Since there are no additional rows, the result is simply the minimum value, which is 5. To summarize, this algorithm maintains the minimum and second minimum values for each row while ensuring the current row's minimum path sum avoids the column of the previous row's minimum. The time complexity is O(n²) because of the nested loops iterating through the rows and columns, while the space complexity is O(1) due to in-place updates. This makes the solution efficient and scalable for larger grids. To analyze the time complexity of this solution, let's first consider the outer loop. This loop iterates through all the rows of the grid, starting from the second row. If the grid has n rows, the outer loop runs n1 times, which we approximate to n4 big O notation. Next, within each iteration of the outer loop, the algorithm processes all columns in the current row to calculate the potential minimum path sum for each column. Since there are n columns, this inner loop runs in O(n) time. In the inner loop, operations such as comparisons or arithmetic updates are constant time operations. When we combine the outer and inner loops, the total time complexity becomes O(n) for the outer loop multiplied by O(n) for the inner loop, resulting in an overall time complexity of O(n²). Now, considering the best, average, and worst cases, the time complexity remains consistent at O(n²), because the algorithm processes each row and column in the grid regardless of the input values. Moving on to space complexity, the algorithm uses a few variables to store information about the previous row, such as the minimum value, the second minimum value, and their respective indices. These variables are updated row by row and require only constant space, or O(1). Additionally, the input grid remains unmodified, and no extra data structures are used, such as additional arrays or matrices. This ensures that the auxiliary space usage is constant. Therefore, the overall space complexity of the solution is O1. If we compare this optimized approach with a brute force or naive solution, the contrast in efficiency becomes clear. A brute force method would involve recursively exploring all possible falling paths row by row, calculating their sums, and finding the minimum. This approach essentially explores all combinations of paths, leading to an exponential time complexity of n*n(n)(n)1. Furthermore, the recursion stack in this naive solution could grow up to O(n) for n rows, increasing the space complexity. In contrast, the optimized solution significantly reduces redundant calculations by tracking only the minimum and second minimum path sums for the previous row. This improvement brings the time complexity down to O(n)², and the space complexity to O1, making it far more efficient. To provide a mathematical proof for the big O analysis, we note that the outer loop iterates n times, and the inner loop processes n columns for each row. This results in a total of n*n=n² iterations. Within the inner loop, the operations, such as comparisons and arithmetic updates, are performed in constant time. As a result, the overall time complexity remains O(n²), dominated by the nested loops. On the space complexity front, since no additional data structures are used and only a constant amount of space is allocated for variables, the space complexity is O1. In summary, the optimized approach achieves a time complexity of O(n²) and a space complexity of O1, making it both time efficient and space efficient when compared to the brute force solution. One of the most common mistakes when solving this type of problem is neglecting edge cases. For example, if the input matrix is empty or has only one row or column, it may lead to runtime errors or incorrect results if not handled properly. It's essential to consider these scenarios during both implementation and testing. Another frequent issue is using inefficient recursive solutions. Without memoization, recursion can lead to excessive recomputation, resulting in exponential time complexity. A good fix is to leverage memoization techniques, such as using a dictionary or a dynamic programming table, to store intermediate results. Finally, incorrect base cases in recursion can cause major problems, such as stack overflow or faulty outputs. For instance, in matrix traversal problems, failing to handle the last row or column appropriately can break your solution. Always ensure your base cases are clearly defined and account for all possible scenarios. Another common oversight is not fully accounting for problem constraints. If you fail to analyze the maximum input size, you might end up with a solution that exceeds time limits, especially in competitive programming or interviews. To address this, always choose algorithms with time complexities that align with the constraints. Additionally, off-by-one errors in indexing are a recurring pitfall. These occur when iterating over arrays or matrices, such as starting from index 1 instead of 0 by mistake, which can result in accessing invalid elements or skipping necessary ones. A helpful strategy is to define clear boundaries for your indices and validate them during development, ensuring accuracy in your loops and conditions. When approaching problems like these, recognizing patterns can be a game changer. Many matrix problems reduce to well-known categories such as dynamic programming, matrix traversal, or even graph traversal. Identifying these patterns early on can help you select the right approach quickly. Equally important is clear communication during interviews. Walk your interviewer through your thought process, explain any trade-offs, and clarify assumptions. This not only demonstrates problem-solving skills but also shows your ability to think critically. Additionally, starting with a brute force solution can be a valuable step. It ensures correctness and provides a foundation to refine your approach iteratively toward an optimal solution. Lastly, be prepared to analyze and explain the time and space complexity of your approach. Interviewers often want to see a deeper understanding of algorithmic efficiency and how your solution scales with input size. There are also related problems on platforms like LeetCode that can help you strengthen your understanding of this topic. For example, LeetCode 931, Minimum Falling Path Sum, is a very similar problem that involves matrix traversal using dynamic programming. LeetCode 62, Unique Paths, focuses on counting paths in a grid and is another excellent example of dynamic programming in action. LeetCode 64, Minimum Path Sum, tackles finding the minimum cost path in a grid, which builds directly on the same principles. Finally, LeetCode 70, Climbing Stairs, is a simpler dynamic programming problem that introduces foundational concepts like recursive patterns and subproblem optimization. Practicing these problems can deepen your understanding and improve your performance on variations of similar challenges. When solving these kinds of problems, there are several alternative approaches you can consider. Using recursion with memoization is a common strategy. This approach explores all paths but avoids redundant calculations by storing intermediate results, significantly improving time complexity over plain recursion. However, it does require extra space to maintain the memoization table. Another option is bottom-up dynamic programming. This method starts with the simplest base cases and iteratively builds solutions to larger subproblems. It's often more space efficient than memoization because it can reuse memory for previous computations. Finally, there's the greedy approach, which works by making locally optimal choices to attempt to arrive at a global solution. While this can be very fast, it's not always applicable, especially if the problem lacks the optimal substructure property. Understanding when each method is appropriate is key to choosing the most effective solution. Great job! To summarize, we explored the minimum falling path sum 2 problem, focusing on dynamic programming for an efficient solution. Remember, dynamic programming helps with optimizing problems involving overlapping subproblems. Keep practicing, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!